Let's tell you what we're going to be working on today. That funny mess is meant to say 1 because I got the wrong digit. Right. We're going to be looking eventually at the indefinite integral. But before that, we're going to look at how do you find the exact area under a curve using Riemann sums. And that's basically the last, whatever, 7, 8 questions from section 5.1. And that'll be the first part of today. I don't know how long it's going to take. Based on the other class, it took about just a little bit over half the time. And then we'll be looking at the shortcut method, because if you want to do it by Riemann sums, it's not an exaggeration that it would take you 20 minutes to just find one exact area under the curve. Very cumbersome, very long. So once we've done one, I think it's question 13, we're just going to say, hey guys, this is a bit laborious. Wouldn't it be nice if there was a shortcut? Remember Calc 1, the shortcut? You know, power rule, all that good stuff. Hey, can we not do that in Svelte? And the answer is yes, we can. And we'll show you how you do it. So I'm going to get kind of off kilter just a tiny bit. Question 9 has been causing some trouble, and this is in 5.1. So let me just talk about question 5.9 for a few. Hopefully you can see it, and get that out the way so that when you come to do it, you don't have such a big problem. Okay. It's pretty standard question, right? It's a table. You're going to use the table to get all the numbers, and you're going to do a right Riemann sum. Do you know that just means R6? Left Riemann sum just means L6. And so if you're wondering about this word Riemann sum, that's essentially all it is. It's just another term that we haven't used much yet. What makes this question awkward, apart from all this stuff up the top, which is more of a distraction than a help, is that if you want to find the area, don't you have a strip and a height, a strip and a height, a strip and a height? But isn't the strip normally delta x and it's the same number? And then it's just all the guys on the left get you the height. Well, in this, there are 2 distinct sneaky parts. First sneaky part. Do you notice that from one number to the next, the interval, i.e. the width, is different sizes? So for instance, see your first rectangle is going to be 10 units long, 0 to 10, 10 that way. And then what height? Well, if you're using a right-hand one, you're going to use the right-hand number, so it's going to be 185. So your first interval is going to be 10 wide, 185 tall. Now what's your next interval going to look like, your next strip? Well, the width is going to be 5. You can see the width is now 5. And the height is going to be the right-hand side. So the next one's going to be 5 times 319. The next one's going to be 5 again, 452. And you're going to say, okay, I got that. You're changing the width on me, so that really means I can't really do a shortcut. I've got to find each strip on its own. Yeah, Sabrina.
I'm not sure if it's just me, but some people are saying in the chat, I'm not seeing the screen right now.
Can you see it? Then it's me, and I will do that again. Let me try it. Can you see it now? Are we having technical issues? Is that screen on the screen? Okay.
Yes.
I don't know what I did wrong there. So, quick recap. Do you notice that the interval sizes right between one number to the next changes? So your rectangle are not going to be the same width. They're not all going to be delta x. The delta x, if you like, changes value each strip. So the first strip is going to be 10 units wide and 185 tall. If you could turn that on its side, you see the right-hand number that you're going to use for it. The height of the rectangle is 185. And then it's going to be 5 times 452. And then it's going to be what later on, 12 times 784. And that takes care of one of the problems. The second problem is this guy. You see, you're being asked to do only 6 intervals. And if you look up somewhere else, it tells you, and I can't see. Oh yeah, here. And you're only interested in the first 62 seconds. So do you see this piece of the table on that bottom row? ignore it totally because it's not going to get used. In fact, I wish it wasn't there. So what you're going to do in that question is you're going to go 10 times 185. Next interval is 5 times 319. 5 again, 452. The next interval is 12 times 274, and so on. And when you've done it, you'll have 6 different strips, and you'll have calculated the width and the height of each, and then you add them up. And after all that hard work, well, according to this one, at least it's that number there, but that's just because that's the answer for that particular table. Yeah, look if your table was the same. And I forget that when I open these things up, I get by default the answers, which is not that helpful for me. Are you okay with that? That first question, that it's just a little bit different because the widths are different, and that's the key. So what we're going to do now is look at Riemann sums, and that's, as I said, the major part. God, I'm jumping around. I'm making you dizzy, making me dizzy. Okay, I've lost the damn thing. Okay, good. Yeah, found the right place. Okay, so what's someone chat asking? Yeah, we fixed that. Okay. So what are these things that we kind of mentioned kind of in passing? What are these Riemann sums? So let me show you a Riemann sum. This is just an example of one just made up. Suppose I did I equals 1 to 10 of I squared. That's an example of a Riemann sum. This symbol here is called sigma. So it's a capital sigma, Greek letter. And you read it like this, the sum, so this is how I would read it out loud. The sum from I equals 1 to I equals 10 of I squared. So if you wanted to read that out loud to someone, you would say it's the sum from I equals 1 to I equals 10 of I squared. So how does it work? Well, this I is called a counting variable. So I equals 1, and you get 1 squared. And then you go to 2, and I equals 2 gets you 2 squared. And then you go 3, and then you go 4, and 5, and 7, and 8, and then you finish with 10 squared. So this Riemann sum is the same thing as this big, long addition. You see, the convenience of having this notation is a lot less clunky than this one, right? So it's a notation that makes it easier for us in mathematics to deal with adding lots of things together. Now, another thing about Riemann sums is that the variable that you use for counting, and in this top question, it was k, as long as you are consistent, this guy mathematically is identical to the first one. Couldn't I say P equals 1 to 10, R equals 1 to 10, any letter of the alphabet? So the letter I believe, tends to get used in this textbook. I've seen a lot of textbooks. If you go online and look, I've seen a lot that use K equals 1 as well. So you might get some other letters I'm not so comfortable with. Are we comfortable with what does that mean? What does this funny notation do? Right. Now that is going to be helpful because when you calculate the area under a curve, don't you add up a whole load of things together? And so it would be helpful if we could write down, using a Riemann sum, how to get R4 or R10. Right. Well, let's see what that looks like. Let's suppose that I have a function, and I'm going to make it very general. I'm going to avoid numbers at every opportunity. So it's just any old function called y equals f of x, and it's going to start at a, It's going to finish at B, and it's going to have some strips. And in fact, it's going to have n strips. Would you agree that's pretty general then? We don't know what the function is. We don't know where to start. We don't know where to finish, except A and B, right? And we don't know how many strips. We're just going to call it n. And we are going to get from that Rn. Well, if I wanted to make that thing or create that, right, a right sum, okay, then wouldn't I set up my table? And I'd start at A. And isn't A called x0? And then the next guy would be called x1. The next guy would be called x2. And wouldn't you finish at xn and he'd happen to be B? Agreed? And this fella here, we could call him f of x0, and this guy will call him f of x1, and then this guy will call him f of x2, and when we go down here, we'll call this guy f of xn. Still good? Now, I want to do an Rn. Well, won't Rn be delta x, the value of the function at x1, plus the value of the function x2, all the way to the value of the function at xn. And the reason for that is that don't you only use these guys, the right-hand side, when you do an Rn? Would you agree? You missed the first term out, and I put a circle on that first one. That's my mistake. You start here, right? And this could be written down as a Riemann sum. It would be sigma I equals 1 to n delta x f of xi. Now let's see why that and this are the same thing. First thing I've done is, do you notice that all those delta x's, couldn't I distribute them back together again? So I could have written this down as delta x f of x1 plus delta x f of x2, and then finish with delta x f of xn. Right. Are you comfortable that this sigma notation is the exact same thing as this linear? We're good with that? Okay, I don't see any shakes of head. So I'd like to make this a little bit more detailed. Well, there are some things I know. Isn't delta x b minus a over n? Agreed? So this fella can be written as sigma I equals 1 to the n f of xi, and I'm just going to put the delta x at the end. So it's looking a little bit better. Wouldn't it be nice if I could find another way of writing down who xi is? And I'd like to be able to use xi, and the only things I want to use are I, a, b, and n, right? Those kinds of things. Let's see if we can make that happen. x1, won't that be a plus delta x? Do you agree? Now, what would x2 be? Well, you'd add another delta x and you'd get two of them. If I have a pretend general guy in the middle, I'm going to call this middle term xi. Wouldn't that be a plus I times delta x? You know, like if I was 7, it'd be x7 would be a plus 7 delta x's, which means that this guy can now be called I equals 1 to n f of a plus I times delta x, b minus a over n. There's just one more thing I'm going to do. I'm not going to call this fella here a plus I delta x. Because don't I know another expression for delta x? What is delta x equal to?
B minus A over N.
You see up there? Yes. So what I have done here, I know it's a lot of pain in the butt to do it, but haven't I described how to get a right sum, an Rn, for any function f of x, starting at any number a, finishing at any number b, and using n strips? Would you agree that would be the guy that would do it? And that is essentially the Riemann sum for every single area under the curve in the universe. Right. The minute you tell me f of x is x cubed and a is 2 and b is 7 and n is 42 strips, can't I then start dealing with it and make a table, right, and do what we do? But we're going to take it a little bit further. We've just discovered, it took a while to get there, that the Riemann sum, right, the Rn value, written as a Riemann sum, ends up being this fella. The value of the function at this point times delta x, which is that guy. Now we're going to do one more jump. I don't want to know the estimate Rn. I don't want to know an estimate for this area under the curve. I want to know the exact answer, right? The real area under the curve. And I'm going to call that area A for the time being. Right. Maybe I'll call it area for the time being. Would it make sense that if I find the limit as n tends to infinity of Rn, wouldn't that eventually become the same thing as the area under the curve? In other words, instead of doing a million strips, I did a billion, trillion, kept on talking till we get to American debt, right? Number of strips. If you made it go infinite, does it seem logical that what you end up with is the area? And that's how we are going to find, for one question, because it takes bloody forever to do, for one question, we're going to use this technique to get the exact area under the curve. So in the example that I've just got, if I write it now down in its full format, instead of Rn, I write this horrible mess. It's going to be the limit as I equals 1 to n, f of a plus b minus a over n I times b minus a over n. And if we can find the limit as n tends to infinity of this ugly guy, we will have found the exact area under the curve. And I'm going to change the notation on here to be the area or the integral from a to b of f of x dx. So we now have a technique for getting exact values. It involves finding the limit as n tends to infinity of Rn. Okay, I'm going to pause for a second, give you a chance to figure out what the heck's going on. Now I'm going to do question 13. In this question, we are being given the function, it's x cubed. And we're going to use this technique to find, pardon me, the area under the curve of x cubed from x equals 0 to x equals 1. Of course, technically speaking, at least right now, it's going to use n strips. So we're going to find the exact area under this curve from 0 to 1. And we're going to do it by using n strips and then making n go infinite. So the integral from 0 to 1 of x cubed dx, right? The area under that curve is going to be the limit as n tends to infinity of sigma I equals 1 to n. The value of the function at this point here times delta x, which is that guy. Okay, let's see what we have here. Would you agree that a is 0 and that b is 1 and that the function that we're going to be using is x cubed? So far, so good. Now, I would like to know what delta x is. So it's b take away a over n, and that happens to be 1 take away 0 over n. So that happens to be 1 over n. Are we happy about that? What delta x is equal to? Okay, I've got all the pieces. Let's plug them in. It's going to be the limit as n tends to infinity, sigma I equals 1 to n, the value of the function at 0 plus b minus a, which is basically delta x, so 1 over n I, times b minus a over n is 1 over n. And that is going to become the limit as n tends to infinity of sigma I equals 1 to n of, well, nothing plus this guy ends up just being the value of the function at I over n times 1 over n. Still with me? You happy about this becomes this and now this becomes this? Okay, the value of the function at I over n, since the function is called x cubed, isn't this I over n cubed? Great. So the next line looks like the limit as n tends to infinity of sigma I equals 1 to n of I over n cubed, right, x cubed, times another 1 over n. And now we get to here. Oops, my sigma went funny. That becomes I cubed. That becomes n cubed times 1 over n. And then one more line, we get to here. Are you following how we got from the y equals x cubed from 0 to 1 using n steps to finding this cell here? Okay. Now, you normally would have said, well, that's it. I don't know what you get if you add I cubed over n to the power of 4 from 1 to n. Who knows what that is? And so they're kind of generous to you. In the question, they tell you this thing. they tell you, and you just say, oh, thank you, I didn't know that. The sigma I cubed is this fella. Now, this guy and that guy aren't quite the same. Do you notice there's a n to the 4 on the bottom? You see that? See that n to the 4? So it's I cubed over n to the 4. Wouldn't it be nice if we could incorporate that? So let's see what that looks like. If this piece here, the I cubed is this, isn't this over n to the 4 just that guy squared all over an n to the 4th? Does that make sense? Are we good with that? Right. Now, I equals 1 to n. Foil that out, or whatever you want to call it, you get that guy. Divided by that gets you that guy. So if you tidy this up a little bit, it ends up looking like that. You know, the 2 squared becomes 4 and it joins that guy. So that's the 4n squared into the 4 comes from. That guy squared, and 2 squared, and then n into the 4. We're good? Right, now, I equals 1 to the n. How about cancelling or partially cancelling those 2 guys? So what I now have is n plus 1 squared over 2n squared. We do a little cancelling, n squareds. We got that. Now we get, foil that out, you have an n squared plus a 2n plus a 1. And darn it in space, I forgot something. The sigmas have disappeared. The sigma killed off in that line. So this expression is quite right, but for some reason, I kept writing sigmas down when I should stop. Maybe you caught that and you were confused.
Wouldn't the denominator of the last equation be 4 because the 1 over 4 never canceled out?
You are correct. Thank you.
Thank you. Just wanted to make sure I wasn't missing something.
No, the fact that you caught it means you're paying attention and you know what the heck's going on. So this is the expression that that thing is equal to. So what we're now pretty much trying to find is what this looks like when n goes infinite. That's actually not too difficult. What's the answer to that limit of this fraction? What's the answer to that? Think back to Calc 1. Remembering doing limits. You could divide the top and bottom by n squared, or you could use L'Hopital. Can you remember doing those things? It would be week 2 of Calc 1. Okay, here goes. If you want to find the limit of a fraction, one of the ways you can do it is you can divide the top and bottom by the same amount. In this case, I'm going to choose n squared. That means that this is the limit as n tends to infinity of 1 plus 2 over n plus 1 over n squared over 4. Okay, then you can replace the n with infinities in wherever it happens to occur, and you should be able to get your answer. Right, on the top, you're going to get 1. What does 2 over infinity look like? What does the limit of 2 over infinity get you?
0.
And doesn't 1 over infinity squared get you zeros?
Yes.
So what you've got here is, I guess, that, but isn't that just a quarter? We have found the exact area under that curve, and it was a quarter. And I wish I hadn't made that mistake of keeping the sigmas going, but fixed it, right?
Could you go over like how the sigma got canceled out?
Sure. We had a question, or we had this part where we had a guy that looked like this. And we were told up here that this guy, right, this piece here, was equal to that. So if you think of what you could do with it, this is another way of looking at it. Would it seem reasonable that since n is a fixed number, right, it has nothing to do with I, so I could bring this out, couldn't I call it that? Does that help to see it that way?
Yeah, that makes sense.
Right. And so what I'm now going to do is replace that guy with the n plus 1 squared thingy all over 2, which is kind of that line there. And so that's how it disappeared.
Okay, thank you.
Well, that one took far too long. Not that
Sorry.
we did anything wrong, but it is a long question. Yes, Bernard.
Can you explain how the I over n became cubed over n?
Yes. When we looked at the original function, it was x cubed. And if you want to find the value of the function at I over n, you're essentially substituting the x with I over n. So you have I over n cubed.
Okay,
And
thank you.
that's where that came from. Good question. Anything else about that? The good news is that's the only one you're ever going to see. And it's actually the homework question, and the answer's a quarter. So that part is easy for you to deal with. But it is the foundation behind why we can do what we're about to do, well, not quite right away, but what we'll be about to be doing over the next day or so. It allows us to find exact areas under curves rather than estimates. I think I've probably convinced you why we don't use this technique. Can you imagine doing 10 questions where you had to go through something like this each time? It wouldn't be fun. But that's the theory behind it. So theoretically, at least, in all the questions that later on I say, hey guys, here's a shortcut way of doing it, you will go and say, thank you for having a shortcut. But if I really had to, and somebody gave me enough money, I could do it the way you showed me right now and still get the answer a quarter, right? But it would be much more onerous job to do it that way. So mathematicians love shortcuts, don't we? Because unlike engineers, we don't like number crunching, most of us. And so we find algebraic ways, shortcuts, to do the same job. Next couple of questions I'm going to deal with is essentially finishing off that homework stuff. I'm trying to see if I've got my guy handy. No, okay, I'll do it again from scratch. Right. If you want to get the area, it's the limit as n tends to infinity of sigma I equals 1 to n, the value of the function a plus b minus a over n I times b minus a over n. Right. So, although you won't be able to see that in a few moments, will you pretend that you've got a copy of it? Maybe it would be a good idea to have a copy because it's going to get used in a different way in a few moments. So let's close this off and show you what the homework questions that we're going to be dealing with look like. By the way, that guy there, hopefully you can see it. You're looking at question 13. That's the guy where the only answer that you had would be a quarter. Okay. And in there would be that big mess that I gave you earlier. Now, let's look at this function here, question 14. I'll make it a bit bigger. The function f of x is going to be x plus ln of x. And the interval is going to be from 3 to 7. And what we're being asked to do is to put inside that box the f of a plus b minus a, all that good stuff, right? So, actually, I think it'd probably be better now for me to go back to the paper. Yeah, I think that would be better. Okay, here's an expression. What number is a?
Three.
3.
Would you agree b is 7?
Yeah.
Right. So if I go over here and I replace everything that's a with a 3 and everything that's b with a 7, won't I basically have the thing that they want me to write down? So let's see what that looks like. It's going to be the limit as n tends to infinity of sigma I equals 1 to n. That bit they actually give you, right? We're basically filling in the middle. So it's the value of the function at a, which is 3, plus, okay, delta x, that's basically delta x here and here. It's b minus a over n. In this case, won't that be 7 take away 3 over n? Won't that be 4 over n? So if you want to know what that fella is, he's 4 over n. So 3 plus 4 over n I times 4 over n. So far, so good. There's the a, that's the b minus a bit, that's the b minus a bit again.
We're doing number 14 on the homework, right?
Yes.
The a value was actually 4.
It will be in, for some people, it'll be 12 and 10.
Oh.
Because WebAssign keeps changing, you know, each person gets their own version of the question. So this is my version, but yours, yeah, could be 48 or 4010 or whatever. Now, that's not quite what they want. They want a little bit more detail. So this is what they do want. The value of the function at this point means that this entire thing, right, this whole piece is basically x. So x gets you 3 plus 4 over ni plus the natural log of, oops, I forgot my 3. 3 plus 4 over ni times a 4 over n. And that guy there, from here to here, is what would fit in the box and you're finished. Can you see how you can take this question and generate this Riemann sum? Now, you're not going to do any more. That's the good news. Can you imagine how horrendous it would be to do about 20 lines of working to simplify that down so that you could eventually make n go infinite and figure out what the number is, right? It would be horrendously bad to do. So they don't ask us to, thankfully. Right, let's look at the next question. Because they do something connected to that, but different. In question 14, oops, let's make sure we're on it. On question 14, didn't we have to fill in that ugly mess I just gave you, the 3 plus 4 over ni thing, right? In this one, they give you the Riemann sum, and you should be able to figure out, just looking at the information in this Riemann sum, what the function is and what the a and the b is, right? Anybody want to tell me what the function is? X to the power of 4, 5, or 6. What do you think it would be looking at question 15?
Power of 5.
I agree. So it's either that guy there, right, or it's that guy there. Great. Now, this fella here says I over n, doesn't it? And because it says I over n, isn't that really 0 plus I over n? So can't I infer from that that a had to be 0? And because it had to be 0, doesn't it make it that one? Are we cool with that? That's pretty much how you would do that one. Let's move on to this one. Okay, a bit messier, a lot more going on. If you look at this function, the bit that's going to tell me who f of x is this piece here. Which one of those guys is the function f of x going to be? It's 1 over 2 plus an ugly thing. That's actually a clue. One over 2 plus an ugly thing.
So that 7i over n is the x.
Yeah. So it's either that one or that one. See, if it said 3 plus ugly thing, it would have been 3 plus x. I'm just calling it ugly thing because I don't want to say 7i over n all the time, right? Next time it'll be 12i over n, 14i over n, you know, look something like that, right? 82 over I and n, right? That's what they look like. Now we have a problem. Is it starting at a 1? Oops, wait a minute. If I get 2. Oh, the little darlings. They are sneaking. Which one are we starting at? 0.
0.
Yes. How did you know it was 0?
Because it's 7 over n.
Yeah,
So B would be 7.
yeah. Oh, yes, shortly. You found an easier way to say it. I was trying to think of a better way to say it, but that one kind of made it. Okay, last guy. Hopefully by the time you've seen the 2 that we've just done, you'll begin to get the feel for this. Which one of the guys there is the square root fella that we're going to work with? What's the function f of x?
The square root of 1 plus x.
Agree. Tell us why. What made you think that? You're right.
Because the expression is, there's no 4 in front of the square root other than the 4 over n.
And doesn't the 4 over n belong with the 4 over n and I? So it's a bit of a distraction. Yeah. So that makes it a 1 plus x guy. So it's this fella here or this fella here. Now she's quite right. Do you notice that 4 over n is also matched here? See if this had said I over n and that had said 4 over n, wouldn't I have picked one of these guys here instead? Okay, so we've decided it's either this fella or it's this fella, right? Which one is it? The 0 to 4 or the negative 4 to 4?
0 and 4.
Agree? Is there a short way that you could explain why you picked that?
Because if it, the difference of the values A and B. this
Okay,
one's A,
so
and
it's like nothing to 4 gets you 4. Is that what you're
Yeah.
thinking?
yeah.
Okay, makes sense. Just wanted to see if, you know, different people see things differently. I just was curious to see how your brain's like. Okay, that is the end of that, guys. So let's tell you, as I guess you already are assuming, that doing Riemann sums is probably not very practical. I mean, if every mathematician had to do one of these horrendous Riemann sums every time they wanted to find an integral, right, an area under the curve, well, things would slow down a lot for starters. And the answer is that we have a shortcut. So the shortcut is called the antiderivative. And right now, I'm just going to tell you how to get an antiderivative. Tomorrow, I'll show you how you use it, which is kind of a little bit different. Right. You have a function, and there's another guy called its antiderivative, which is very often called capital F of x. Can you remember doing the end of Calc 1, where you found antiderivatives? It would be the last thing you typically do in Calc 1. Can you remember those guys? Vaguely? Okay, let's put some numbers in. If you had x cubed, its antiderivative would be 1/4 x to the 4. The antiderivative is the opposite of differentiation. So what you're wanting to say to yourself is, what function would I need so that its derivative would be x cubed, right? So what function would I need to start with whose derivative would be x cubed? Would you agree if you differentiate this guy, you get x cubed? So this is the antiderivative. What would the antiderivative of 4x to the 5 get you? Anybody want to volunteer that one? 4x to the 5.
Is it 4/6 to the 6th power?
Yep. And we'd probably turn the 4/6 into 2/3, but let's just leave it as 4/6 for the time being. Now let's generalize it. I want to find the antiderivative, that's what this guy's called, of any multiple of a power, like 7x cubed, 10x to the 20th. You add 1 to the power and you divide by the new power. So let's see how that works. You add 1 to the power and then you divide by 4. You add 1 to the power and then you divide by 6. You add 1 to the power and then you divide by. This is called the power rule. Isn't there a power rule for differentiation as well? It's a different rule, but it's called the power rule. You remember that one? How do you differentiate x to the 7? Isn't it multiply by 7 and reduce by 1? So 7x6, that kind of thing, right? Try not to get too caught on that because we want to focus on antiderivatives today, right? How about the antiderivative of sine x? What function would you need to start with whose derivative would get you sine x? Be careful with your signs.
Negative cosine x?
Correct. What would the antiderivative of cosine x be?
Sin x.
Have you noticed that it's kind of like differentiation, but different as well? Because isn't this an antiderivative, right? It's the opposite of differentiation. So you'd expect things to be kind of turned, back to front. This one is for those people who have very good memories. What is the antiderivative of secant squared x?
Tangent.
What? Yes, tangent. Well done. This one's even worse. What is the antiderivative of a secant tan?
Secant?
Yes, quite hesitant, but yes, you're right. Anything that you've met or found in Calc 1 doesn't disappear because you're now in Calc 2. Things move from one math class to the next. You have not finished factoring things. You have not finished differentiating things or solving equations for that matter. So you gotta try and not put a box when you finish a class, lock the key and throw it over your shoulder and say, phew, Calc 1's out the way, I can forget about that now. That's kind of not how it works with math. Now let's put in a baby one. My favorite function.
The x.
Yeah. Are we good? What about 4?
X.
Almost. Not just x,
4x.
4x. Agreed? You need the 4 as well. What about 1 over x? We'll have to finish here. What? 1 over x, last one for today.
That is just it.
1.
Oh, I've had, that is just x and that is 1. Keep thinking. I want to hear the right answer. What function do you need that when you differentiate this function, you get 1 over x? That's what we're after.
Natural log of x.
That's the darn one. Yes.